So, let us delve a little bit deeper into multi-rate operations. One of the questions that we get in our mind is, can we swap the downsamplers and the upsamplers? It might be useful for some reason first to slash the sampling rate and then expand, or maybe expand first and then downsample, right? Under what conditions can we swap these operations? So, that is an interesting an idea in itself that leads us to these interconnecting systems. So, we have a signal x of n we downsample this first by a factor of m and then upsample this by a factor of L, and we get, say suppose a signal y1 of n, let us say this is case A. The second case we take the same input, but we do the other way around, upsample by a factor of L followed by downsampling by a factor of m, and we get the signal y2 of n, and this is say B. The question is, are A and B equivalent? Of course, a trivial operation would be upsample by L and downsample by L. I mean, they are not doing anything there, right? That is a very trivial operation. So, there is a theorem which links this scenario, and the theorem is stated as follows. The systems A and B are equivalent if L and M are relatively prime. That is GCD of L comma M equals 1. So, I will basically sketch the proof because it has a small detail which I want you to work as a homework exercise. Okay. Now, y1 of z is the frequency domain response, and basically z transform of the signal y1 of n, which is 1 upon m summa k equals 0 to m minus 1 x of z power L upon m omega m power k. Now, how did we get this? Basically, you have a factor z power L. So, first you look at the interim signal which is at this step, because you have x of n and you are downsampling it by m. So, you have a factor of 1 upon m, you have m copies, and then you are looking at the translates of all these copies, right, and then you have this z power 1 over m factor and omega power k. This is for the translation, and then this is basically for the stretch 1 upon m, right, and then that interim signal, when it is going through an L fold expander, you have a factor of L that appears here. So, this is basically straightforward. and then similarly we do y for y2 of n, and we get y2 of z is 1 upon m summa k equals 0 to m minus 1. At the very first step we have x of z power l to start with. So therefore we have x of z power l upon m, and this is omega m power k times l. Now there is a little bit of detail here. So y1 and y2 seem almost the same, except that if you observe at these modulation factors, one set is omega m power k, the other set is omega m power k times l. That is the only difference, right. So now if we ensure that both of them are equivalent or the sets are the same, then I think we are proving that these two systems are identical. So I will put this as a claim which is part of your homework. The set of numbers, these are all complex quantities, S1 comprising of omega m power k, these are basically distinct mth roots of unity, and this set S2 which is omega m power k times l, right, for 0 less than or equal to k less than or equal to m minus 1, is equal if and only if GCD of L comma m equals 1. If the GCD of L comma m equals 1, then this set of numbers are equivalent. You can do a simple test. I mean, you can choose L equals 2, m equals 3, and then look at all the roots here, and at least get an intuitive feel if the sets are the same, right. And once you get this feel, I think just start with trying to expand this relationship for GCD of L comma m equals 1 more carefully in precise math form, and then prove this result formally. So it is not too difficult. I have just given this as a homework exercise so that you can work this out. So now we know that we could interchange the decimation process and the expansion process, provided the GCD of L comma m equals 1, right. So we will delve into the next concept, which is on Nobel identities. So one can ponder about what is noble about these identities, but we will see they have some interesting consequences. So the idea behind Nobel identities is, can we link downsampling followed by filtering to perhaps filtering with downsampling, like the way we did swapping of operations for downsampling and upsampling, possibilities when they are equivalent up to swaps. The question sort of can be extended if we can do downsampling followed by filtering, as possibly filtering first and then downsampling. Similarly, if we are filtering and then upsampling, in what sense is it equivalent to upsampling first and then filtering, so on and so forth, right. So, these are two questions, and fortunately we have answers to these, and that is part of Nobel identities here. So, let us consider the first case. We are downsampling by m followed by filtering, and let us say this interim signal is y 1 of n, and the question is if this is equivalent to filtering first through some filter followed by downsampling. And similarly, we have another case here. Where we filter first and then upsample, and we are wondering if this is equivalent to upsampling followed by some filter, not necessarily the original filter that we started with. So, before we get an idea to formally prove this, we have to see if this result makes sense, right. And I will call this a pathological case. Suppose g of z is irrational, that is g of z is of the form z power minus half, and I think what is important for you to interpret this as basically a fractional delay filter. Now, let us consider the first case itself, this downsampling operation. If x of n is such that x of 2n is 0, that is every alternate sample is 0. Right, y1 is not, and let us assume that m equals 2 here, right, m equals 2, and let us assume that x of n is such that x of 2n is 0. Let us look at the first case. If you are downsampling by 2, right, you are throwing away all the zeros anyway, and whatever you have is basically filtered through g of z. So, y1 is not 0 for all n, I would say necessarily. I mean, at some points you may get zeros, but it is not that for all n y1 of n is 0, right. Y1 of n is not 0 necessarily for all n, right. Some cases it can be 0 and it is not necessary that for all n it has to be 0. But let us look at the case for y2n. Right, y2n, now you have a z power minus 1 here. That means we are taking the signal x of n, we are filtering it through a unit delay, and when we are doing the filtering through a unit delay and then downsampling by 2, you are getting everything to be 0, right. So y2 f n is 0 for every n. So just observe the two cases here. So which basically means that these two operations are not the same if we have to deal with filters which are irrational, and you interpret these irrational power that is irrational in irrationality in these transfer functions as basically fractional delay filters, right. And this is the pathological case, but outside of this pathological case the systems are equivalent, and we will show this by evaluating the Z transform of the signal at the output of each of the systems. Okay. Now we will do the proof. This is basically non-irrational case. So let us consider case A. Now y2 of z is basically, so first you have your filtering with g of z power m, and then this is followed by decimation. So y2 of z is basically 1 upon m, you sum m copies of x of z power 1 upon m omega power k times g of z power 1 upon m omega power k whole upon m, right. And this is a detail that you have to note, because the downsampler is over this filter g of z power m. So there is a modulation here and z power m. Okay. Now this can be simplified as 1 upon m k equals 0 to m minus 1. This term would be remaining the way it is, and this is basically g of z, because omega, you can put a factor m if you want to here, but it's implied, and omega m power k times m, this is basically it is unity, right. So therefore this is just going to be g of z. And let us look at y1 of z. Y1 of z is basically, you first look at the output of the decimation. So the system transfer function is basically straightforward. The output response is pretty straightforward. You have a scale factor of 1 upon m. You have to add those m copies that are basically stretched and translated, right. And now this times g of z is basically the overall response, right, overall frequency response. So from these two equations, say I call this 1, I call this 2, we can infer y1 of z is y2 of z, right. So, basically I can replace a downsampler followed by a filter through possibly a filter and a downsampler, and the filter is basically linked to the original decimation filter as it has to be g of z power m, right. So, now let us do this for the second case. So, we have y4 of z is basically g of z power L times x of z power L. Why? Because you have x of n going through an upsampler, and that system can be replaced as x of z power L, and then x of z power L times g of z power L is what you have for y4, and y3 of z is basically now you have x of z times g of z, it's equivalent to passing this through this upsampler, and which is basically x of z power L g of z power L, right. X of n filtering to g of z is basically x of z times g of z, and that if you upsample, pass it through an upsampler, I mean you can this is equivalent to this relationship. So, now from 3 and 4 y3 of z is y4 of z. And we have showed that these identities are correct or they are true. Okay. So, the pathological case would have arose if you started, I mean if you just started off with writing it normally, just I mean in the proof when we looked at the verification steps, right, we just did not assume any irrationality here as we were just doing the algebra in a routine way, right. But the moment you ponder about these fractional powers, then I think that becomes very important. Then you will see that there is a case if g of z trivially happens to be a fractional delay filter, then they are not equivalent, and then the whole result basically does not work out. Okay, this is a very important step. So, they work with filters that are not fractional delays.